hope that if you've learned nothing else in the last sort of session that we had, was that we've got these two processes, immobilization or photosynthesis. And photosynthesis or immobilization doesn't just have to be photosynthesis, but we've got the photosynthesis going on one way. Okay, and then respiration or decomposition. And those are important processes. You can't just have one and not have the other. So part of our being able to manage ecosystems, however small, it might be as small as the garden or it might be a national park. We want to understand these processes. For instance, in the winter, we're not going to see much of this, and actually we're not going to see much of this. In spring, before we see a lot of photosynthesis, we see a lot of decomposition happening, mineralization of nutrients. You've got this flush of nutrients that comes in. Oh, there comes the sunlight, there comes the warmth. Okay, so it's a cycle. So maybe we need to look at it rather as a cycle than a linear process. But one of the things I wanted to talk to you about was there was a guy called Redfield who was an aquatic scientist. Anyone heard of this guy? Okay, Redfield. Basically, Redfield did research on algae, and he found kind of this, in most algae, he would find sort of these molar ratios, C to N to P. Let's see if I can remember this. I think 106, no, I'm not going to, I'm going to get my cheat sheet out. 116 to 1, carbon, nitrogen to phosphorus. And he found that, there was this very, very, very consistent ratio when he looked at a particular kind of algae in the water. And basically, the C to N ratio over here is approximately 14 to 1. And basically, he found in aquatic systems was that if the N to P ratio, simplifying, if the N to P ratio was less than about 20, then the system would basically be nitrogen, the limiting nutrient. Would be nitrogen. Okay. If N to P is greater than 25, limiting nutrient was phosphorus. In other words, basically what he was saying, when you've got a low N to P, when you've got a low N to P ratio, it seemed like the amount of phosphorus that you had in that water body didn't make any difference to the algal production in the water. So you could add as much, remember Liebig's law of the minimum? For instance, if you had a bunch of phosphorus but not enough nitrogen in the system, you could add all the phosphorus you want. It wouldn't make any difference because your nitrogen was a limiting nutrient. Well, he found the same thing in aquatic systems, that you could have phosphorus limiting or nitrogen limiting aquatic systems. Now, basically what we find in soils is that there are some similar relationships. Basically, soil organic matter has somewhere around about 186 to 13 to 1 ratio of N, P, and K. All right? And so the C, sorry, not NP, CNP, excuse me, CNP This is by molecule, not by weight. Nitrogen and phosphorus, nitrogen and carbon, nitrogen's molecular weight is 14 and carbon's is 12. So molecular weight, by molecule or by mass, it doesn't really matter. Okay, but the C to N ratio here is approximately 14. But we found in soil microbes, this is an interesting one. We've got approximately 60 to 7 to 1. C to N ratio here is approximately 8. So a fairly high carbon to nitrogen ratio. Let me ask you guys, anyone ever worked like in the yard or made a compost pile or something like that? Anyone's dad make compost piles?
My mother, yeah.
Your mother makes compost piles. What's she throw in that compost pile?
Stuff like grass clippings.
Okay, grass clippings. Okay. What else?
Dead leaves.
Leaves. Dead leaves. So, oh, nice fall leaves. Okay. What else? What would you throw in a compost pile?
Food waste.
Food waste, yeah. So we've got potato chips and an old sausage that was left behind, yeah. Edwige, what else would you throw in there? When you go to Starbucks, what does Starbucks give you? I usually get coffee at Starbucks. I know that's a dumb question. Okay.
Tea bags.
Tea bags. Okay, so you put little tea bags in, or coffee grounds. Okay, let me throw that in. Okay, hypothetically, just instinctively, if I had to have a compost pile just made up of dry leaves, how is that going to work if I sort of add water to that and just have the dry leaves? Is it going to decompose really quickly?
I don't think it would.
Okay, all right. How about if I threw a dead squirrel? Just hypothetically, I threw a dead squirrel in that. Would the dead squirrel decompose before the dead leaves?
I think it probably would.
At a faster rate.
It would decompose more quickly.
Yeah.
Okay, so the dead squirrel, here's the little squirrel. Okay, there's his little teeth. Okay. The dead squirrel is going to decompose really, really quickly. When we put food waste in, okay, the secret over here is, not N to P, C. Sorry, if you look in your class syllabus, I said N to P ratio. I talked about it's actually C to N ratio, so forgive me for that. The secret lies in the C to N ratio. So the dead squirrel's cytoplasm is going to probably have a 8 to 1 C to N ratio. Obviously, his bones and his fur is going to have much higher. So the first thing that decomposes in a squirrel, it's going to be his liver and the insides, and then eventually the skin, and then eventually the bones are going to be left last. Okay, and the same thing. Leaf litter or leaves, dead leaves that have been dead for a long time might have a C to N ratio, so leaves of about 100 to 1. Okay, very, very high C to N ratio. Food waste, probably, I don't know, maybe 18 to 1. Coffee grounds from Starbucks, officially 16 to 1. Okay, so we find that there are these different levels, and so if you start mixing all of these things up, but you mix things that have very, very low C to N ratios in, you'll find that compost heap gets hot very quickly. We'll probably, do the McLams have some nice mounds of wood chips at the moment? Okay, what Eric and Robbie McLam have is they get these mounds of wood chips there. They've got a buddy who's in the landscaping industry. he puts lots and lots of wood through the chipper, he chips it up, and instead of taking it to the landfill, he brings it to Robbie and Eric. Robbie goes out to, give me a couple of what's the health food store, the
Whole food.
Whole Foods, no, is it Whole Foods? All right, let's call it Whole Foods. And he comes back from Whole Foods with several 50-gallon buckets full of like old vegetables, vegetables that either weren't sold or leaves and stuff like that. And he takes those buckets and he pours it out there, and then what he really likes to do is he comes in with his front end loader, okay, and he goes in, he mixes this up, because really what he likes is he likes driving the tractor. So he takes these food scraps and he mixes them up with this big old thing. You come back later, 3 or 4 weeks later, he adds some water. You come back several weeks later, or not even several weeks later, but several days later, you put your hand in there, you're going to hurt your hand because it's that hot. So in the mornings you come and you see the steam rising off that. Okay, so what's happening is we have the process of decomposition happening in this. Dead wood with a very, very high carbon to nitrogen ratio, maybe 120:1, but mixed with these greens from the grocery store and water, perfect combination, they start to break down, okay, and the decomposition process takes place. If you could see CO2, you would see a cloud of CO2 gas coming off over there. But what's left behind now is, ammonium. Hopefully not too much nitrate is lost, that might get immobilized. But what happens is you develop this huge microbial biomass inside here. Okay, so why am I telling you all this? We went to the back instead of the front. So soil microbes have about a C to N ratio of something like 8:1. The literature, and I don't want to get too stuck on numbers over here, but the literature says that, give me a minute, a soil microbe, when it consumes something, uses about 16 carbons for metabolism, another 8 carbons for maintenance, and another 1 nitrogen for maintenance. Okay, the nitrogen usually becomes something structural. Okay, so this microbe will then consume that, and essentially that ratio then is around about 24:1. And so we have found empirically that if you have a compost pile or something like a compost pile, and your carbon to nitrogen ratio is 24:1, you'll find some reaction, quite a lot of reaction going on. There's a little bit of warmth. When you lower that, say to 11:1, you increase that rate of reaction. So what happens in this case is that there is a lot of, that's your C to N ratio, there is a lot of excess nitrogen in the system. So let's do this. C to N ratio 24, greater than 24, less than 24. Okay. So we've got these soil microbes munching away. If they munch away at something with a C to N ratio less than 24, they will still be consuming. They'll need the carbon for the energy, and the carbon for the metabolism. So what's going to be in excess when your C/N ratio is less than 24? Will it be the carbon or the nitrogen?
Nitrogen?
Nitrogen is in excess. So in that compost pile, if we put a lot of those green leaves on, we will find that a lot of, if you look, a lot of ammonia, organic N, which we can now measure as well, ammonium and nitrates become available to the soil. Under circumstances where C/N ratios in the soil are less than 24, these become available. We find that N-min, nitrogen mineralization, takes place. And who's the beneficiary of that? The plants, right? The plants then benefit from that. If my carbon to nitrogen ratio is, say, 80:1, let's say I've put a wood mulch around over here, which element is going to be in excess over here? Carbon. Okay, carbon is going to be, by the way, over here, carbon's not necessarily going to be in short supply. It'll just mean that that carbon will be consumed much quicker. Over here, carbon is in excess. Nitrogen is in short supply. These microbes are much better than plants at getting hold of any new nitrogen that comes into the system. That means that any nitrogen comes in, the first organisms to get hold of that nitrogen is the microbes. That means there is an N shortage. Well, first of all, if the microbes are munching those nitrogen, any new nitrogen that comes into the system, what is that process called?
Immobilization.
They are immobilizing. They're immobilizing N. Okay. I know I've repeated it over and over again. It's like, really, is he going to ask us that again? But I want to make sure that you understand it. Okay, they're immobilizing N, and as a result is that there's a shortage of N for plants. So if you put a lot of mulch, say, around a plant that may not be well fed underneath, you'll find that all of the microbes get hold of that carbon in the straw or the wood mulch or something, but they will then be consuming all of the nitrogen that was in the soil pore space as well. And we'll talk about that in a minute, because it'll be organic nitrogen, ammonium, and NO2 as well. So this magic number, it's kind of 20 to 25 carbon to nitrogen ratio that you're looking at. Below that, you will find the rate of mineralization of nitrogen takes place. In other words, things that have nitrogen in them are getting broken down. Because they're not needed by those soil organisms, they're made available to the soil environment to be taken up by plants. Is that kind of clear over there, carbon to nitrogen ratios? I'll give you some literature, sort of fairly simple literature to look over on that. But it's an important concept. Again, it's a concept that we use. Your mom uses it. She might just, it's just, you know, you have this amount of green, this amount of brown, and that's kind of, so there might be a very qualitative way that she does it, but it's still good science, even though it might still be qualitative. Okay, so carbon to nitrogen ratio is part of that biogeochemical concept that we're talking about. Mineralization, when that C/N ratio is low. Immobilization, when that C/N ratio is high. Questions on that so far? Okay. Well, we might as well talk about the Haney soil analyses. One of the things that we've done is in the soils disciplines in the last 60 years is we've given a lot of lip service. Oh, soil organic matter is really important. It's, soil quality is really good. But we've never gone ahead and actually quantified it. And the reason why we haven't quantified it is because it's difficult. It's difficult to come up with ways to quantify the amount of carbon in the soil, the amount of, and how that benefits the plant. I mean, how much organic matter is enough? How much organic matter should I have in my soils? And the answer is, that depends. I don't know. Just try and add more. Should I be putting more effort into putting organic matter in the soils? There's a guy called Haney, who I had the privilege of meeting, and you can look at some of his stuff. I mean, he's a complete maverick. He is an academic now, but he was a farmer and a mechanic at one stage. So he's a real character. But we talked about some of his tests, and I've had City Roots soils tested quite some time with him. For the last, who knows how many years, most soil test labs, most land-grant soil test labs, so Clemson is our land-grant university, you send your soil test, they do P, K, micronutrients, PK, Mg, and micronutrients, and they do organic matter. And usually organic matter, you can get organic matter from different ways, but organic matter, usually you take it, you throw it into a muffle furnace for 24 hours at 500 degrees, and you burn off all the organic matter. You weigh it before, you dry it, you weigh it before, you weigh it after, and the difference then is what you call organic matter. Organic matter sort of is about 3% in a good soil, undisturbed soil in South Carolina. We talked about that. And most places measure organic matter, but if you look at the soil, what is this? If you look at the soil particle, you might find there's your organic matter. It might look like this. So you've got mineral particles and particles of organic matter and that kind of thing. When you look at that from a if you're thinking like a microbe, from a microbe's perspective, that's your house. The minerals and the organic matter, that's your house. So when I'm measuring organic matter, it's not a bad measurement, I can still continue, but it's not measuring my food, okay? And it's not measuring my microbial activity either. Haney has invented, along with a guy called Brinton, a 24-hour CO2 burst. How much time do we still have?
15 or
No, that's not the right time.
It's about 10 after.
10 after 4, so we've got like, what, 15 minutes? 10 minutes. 10 minutes. It says 10 minutes. 24-hour CO2 burst test. Basically, you take a sample of soil, you take 40 grams, you put it, you first dry it at 50 degrees over 24 hours, you put it in a beaker, and you put a little paddle in. The paddle passively measures CO2. It's got a little gel on it, and over 24 hours, it will measure how much CO2 comes in. Obviously, you screw this shut. Your CO2 is generated, and you can passively measure how much CO2 is generated in that. This gives you an indication of biological activity. The CO2 generated from that is an indication of your active carbon fraction in the soil. okay? And in fact, what we can do is there is a good relationship between CO2, 24-hour CO2, and N-min for 1 year. And that's never been quantified before. So this is kind of the result of about 20 to 30 years work in the United States, but started off with the Russians about 100 years ago. We just didn't have the instrumentation that we have right now. And so being able to measure soil respiration, especially that burst, and we'll talk about it next week, is really, really important as a function of how that soil looks like. I've also basically seen sort of organic matter and CO2, you know, there's a good correlation. In other words, if you've got a lot of house, you're going to have a lot of people living in those houses, okay? So Haney also looks at something called water extractable organic carbon and water extractable organic nitrogen. And this is basically in the pore space, obviously, you know, 40 to 60% of the pore space is full of water. And what he's done is he's found a way to extract the from the soil the water extractable carbon and nitrogen. These are things like basically glycoproteins, sugar proteins, both the carbon and the nitrogen. And this WEOC is really glycoproteins. And this is really an indication of food for microbes. Do you remember what Christine Nichols said about carbon? It is the something currency for all soil microbes.
She called it food currency.
The energy currency. She said it was the energy currency of soil microbes. Okay, it's the food over here. Okay, and water extractable organic nitrogen is over here. What is found, surprise, surprise, if that water extractable carbon to nitrogen ratio is less than 20, he's not finding much mineralization in here. Okay, so when it's greater, greater than 20, when C2N is less than 20, in other words, there's a lot of nitrogen around, he does find nitrogen mineralization. So it's exciting because now we're able to actually look at the nitrogen in there. Typically, what we found in city root soils is water extractable organic carbon, 200 to 700 ppm. Okay, the amount of organic matter might be closer to 500,000 ppm if you had to read the actual solids. Okay, water extractable organic nitrogen is around about 17 ppm. Ammonium is typically about 5 ppm. And nitrates are somewhere between 5 and 25 ppm. So now we're able to look at not only the inorganic pools of nitrogen, but also the water extractable, the organic nitrogen pools, because that organic nitrogen is going to ammonify, it's going to break down into ammonium, and then from there to nitrates. Okay, and we're going to look at that a little bit more closely. We're going to take some samples, but I've already got those analyses, and we'll look at that next week as we go on. Questions on this, apart from can we go on? Okay.